The moon has always held a special place in human imagination, shining as the most prominent object in the night sky and shaping the rhythms of life on Earth. It is Earth's only natural satellite, a constant companion that has influenced culture, science, and exploration for thousands of years. From inspiring myths and poetry to guiding early calendars and navigation, the moon has been both a mystery and a beacon. Yet beyond its beauty lies immense scientific importance. Its gravitational pull governs the tides, its steadying influence stabilizes Earth's tilt, and its surface preserves a record of the solar system's earliest history. With no atmosphere, no weather, and an ancient, cratered face, the moon offers a glimpse into the past, while also serving as a stepping stone for the future of space exploration. Studying the moon is not simply about understanding a distant world. It is about understanding our own planet's history, our place in the cosmos, and the possibilities that lie ahead. The moon lies at an average distance of about 384,400 kilometers, or 238,855 miles, from our planet. This span of space is vast enough to make the moon seem remote and unreachable to the naked eye, yet close enough for it to dominate our sky with a steady presence. The distance is a delicate balance, one that allows the moon to circle Earth in a predictable orbit while exerting a profound influence on our planet. It is far enough to float in silent separation, yet close enough to affect the oceans, the seasons, and even the imagination of humankind. To grasp the scale of this distance, one might compare it to more familiar measures. Light, traveling at nearly 300,000 kilometers per second, takes just a little over 1 second to reach Earth from the moon. A modern spacecraft, however, takes about 3 days to cover the journey. If one were to drive a car continuously at highway speed, it would take well over 4 months to travel the distance. This mixture of nearness and remoteness is part of the moon's fascination. It is beyond the reach of ordinary life, yet it remains the most accessible object in space, the only world that humans have physically visited beyond Earth. The average distance of 384,400 kilometers is not fixed but slightly variable. The moon follows an elliptical orbit, which means it is sometimes closer and sometimes farther from Earth. At its nearest point, or perigee, it can be about 356,000 kilometers away, while at its farthest, or apogee, it can stretch out to around 406,000 kilometers. This change in distance is perceptible from the ground. When the moon is near perigee during a full phase, it appears larger and brighter, creating what is popularly called a supermoon. When it is farther away, it seems smaller, giving rise to more subtle displays. The fluctuation reminds us that the moon's journey around Earth is not perfectly uniform but dynamic, shaped by gravitational interactions with Earth and even with the Sun. This distance also plays a critical role in the relationship between Earth and Moon. If the moon were significantly closer, its gravitational pull would cause extreme tides, perhaps so severe that coastal life and human civilization would have been shaped very differently. If it were much farther away, the tides would be too weak to create the rich intertidal zones that foster biodiversity. Furthermore, the moon's gravitational bond helps stabilize the tilt of Earth's axis. At its current distance, this influence maintains a steady rhythm to the seasons, preventing wild swings that might have hindered the development of life. The exact span of 384,400 kilometers, then, is not just a number but a condition that has helped create the Earth we know. For humans, the distance has long been both a challenge and an inspiration. Before the age of spaceflight, the moon's remoteness symbolized the limits of human reach. Ancient cultures told stories of gods and spirits inhabiting the lunar realm, partly because it was visible yet unattainable. When technology advanced, that very distance became a goal to be conquered. The Apollo missions of the 1960s and 70s transformed the abstract figure into a lived reality. Astronauts traveled across that gulf, carrying with them the knowledge that they were bridging nearly 400,000 kilometers of emptiness. Their journeys proved that the moon's distance, though immense, was not insurmountable. Even today, the number remains a reminder of both human limits and possibilities. Robotic missions still traverse that space, and new plans are underway for humans to return. The distance requires careful calculation of fuel, timing, and communication, yet it is short enough in cosmic terms to make repeated exploration feasible. Unlike Mars or the outer planets, the moon's proximity allows us to envision sustained visits and even the possibility of a permanent human presence. The 384,400 kilometers become not just a gap to cross but a bridge to a wider universe. In its silence and constancy, the moon continues to orbit at that average distance, a faithful companion bound to Earth by gravity. The figure of 384,400 kilometers is more than a measurement. It is a symbol of separation and connection, a span that preserves the moon's mystery while making it accessible to science and exploration. From the pull of tides to the footprints left on its dust, everything we know of the moon is shaped by that distance, a gulf that both separates and binds two worlds. The moon is the only natural satellite of the Earth, and it has held a place of wonder, mystery, and scientific fascination for as long as human beings have looked up at the night sky. Unlike the planets, which wander slowly across the background of stars, the moon is a constant companion to the Earth, orbiting steadily and predictably. Its presence is so familiar that it often seems ordinary. Yet the truth is that our relationship with the moon is extraordinary. No other planet in our solar system, except for Pluto with its relatively large companion Charon, has a satellite so proportionally massive compared to its own size. The Earth and Moon are therefore more like a double system than a simple planet and satellite, bound together in a celestial dance that has lasted for billions of years. The Moon is thought to have formed about 4.5 billion years ago, shortly after the birth of the solar system, most likely from the debris left after a colossal impact between the young Earth and a Mars-sized body. This theory, known as the giant impact hypothesis, explains not only the Moon's size but also its composition, which is remarkably similar to Earth's outer layers. From that violent beginning, the Moon coalesced and settled into orbit around Earth, shaping not only the history of the planet, but also the conditions for life. Its gravitational influence stabilizes the tilt of Earth's axis, which in turn helps regulate the cycles of climate and seasons. Without the Moon, Earth might wobble chaotically, leading to dramatic changes in weather patterns that could make life as we know it far more difficult. The most obvious effect of the Moon's presence is seen in the tides. The pull of its gravity on Earth's oceans produces the regular rise and fall of sea levels that coastal communities have observed since antiquity. These tides were not just natural phenomena to be noted. They became critical to navigation, fishing, and even the rhythm of daily life in human societies. On a deeper timescale, some scientists suggest that tidal activity may have played a crucial role in the early development of life, creating dynamic environments where simple organisms could adapt and evolve. The Moon, silent and distant, may thus have contributed to the very spark of life on Earth. For human culture, the Moon has been more than a scientific fact. It has been a symbol, a muse, and a measure of time. Ancient calendars were often based on lunar cycles, dividing the year into months that corresponded to the phases of the Moon. Myths and legends around the world have woven stories of lunar gods and goddesses, of transformations under moonlight, of cycles of death and rebirth linked to its waxing and waning. The moon has inspired poets to write verses about longing and solitude, and artists to capture its glow on canvas. Even today, when its nature is well understood, it continues to stir the imagination of dreamers and scientists alike. In the modern era, the moon became the target of human exploration. The 20th century brought about the space race, culminating in the Apollo missions, when astronauts set foot on its dusty surface for the first time in 1969. Those journeys were not only feats of engineering and courage, but also symbolic milestones for humanity, demonstrating that we could extend our reach beyond Earth. The photographs of our small blue planet rising over the moon's horizon forever changed how people viewed their place in the universe. The moon, once an unreachable sphere, became a reminder of both our limitations and our potential. Though it is the Earth's only natural satellite, the moon is far from a simple companion. It is a regulator of climates, a shaper of tides, a witness to planetary history, and a mirror of human culture. Its influence extends beyond its orbit, touching science, myth, art, and the very conditions that allow us to exist. The fact that the Earth has one moon might appear to be a bare astronomical truth, but behind that truth lies a profound story of connection. To know the moon is to understand more deeply the Earth itself, and to realize that even the most familiar object in the night sky still holds secrets worth exploring. The moon is remarkable not just because of its presence, but because of its proportions in relation to our planet. It is about 1/4 the size of Earth in diameter, yet it contains only 1/80th of Earth's mass. This fact highlights the unique relationship between the two bodies and reveals much about the moon's nature and origins. At first glance, one might imagine that if the moon is roughly 1/4 the size of Earth, its mass would scale in a similar way. Yet mass is not only about size but also about density and composition. The moon's relatively small mass compared to its size indicates that it is much less dense than Earth, and this difference has profound implications for how it formed and how it behaves in orbit. The disparity between size and mass is best understood by considering the materials that make up each body. Earth has a dense metallic core rich in iron and nickel, surrounded by a thick mantle and crust. This structure gives it an average density much higher than that of the moon. The moon, on the other hand, appears to lack a substantial iron core, and instead it is composed largely of lighter silicate rocks. This lighter composition explains why it is not as massive as its size might suggest. When scientists examine this relationship, it strengthens the hypothesis that the moon formed from the outer layers of the Earth after a giant collision in the early history of the solar system. In such a scenario, the heavy metals remained within Earth, while lighter materials were thrown into space and eventually coalesced to form the moon. The contrast in density and mass between the two bodies thus tells a story of violence and creation, showing that the moon is not simply a miniature version of Earth, but rather a fragment shaped by cosmic chance. Because the moon has so little mass relative to Earth, its gravitational pull is also far weaker. On the moon's surface, gravity is only about 1/6 as strong as on Earth. This reduced gravity has a number of important consequences. It means that rocks and dust are not held together as tightly, producing a surface covered in loose, fine material known as regolith, created by billions of years of meteorite impacts. It also means that the moon cannot hold on to a thick atmosphere. Unlike Earth, which retains air and water through its stronger gravitational field, the moon's slight pull allows gases to escape easily into space. As a result, the moon is airless, silent, and exposed, its surface marked by craters that remain preserved for eons because there is no wind or rain to erase them. The relationship between size and mass thus explains much of the moon's stark and haunting appearance. The mass difference also shapes the gravitational bond between Earth and Moon. While the Moon is relatively small compared to Earth, it is still large enough to exert a noticeable influence. Its pull causes the tides in Earth's oceans, a phenomenon that has shaped ecosystems, human activity, and perhaps even the emergence of life itself. If the Moon had been more massive, the tides would be stronger and more disruptive. If it had been less massive, the tides might be too weak to create the dynamic environments that scientists believe fostered early biological evolution. The Moon's exact mass, despite being just 1/80th of Earth's, strikes a balance that has helped make Earth the thriving world it is today. The ratio of size to mass also makes the Earth-Moon system unusual when compared to other planets and their satellites. Most moons are tiny in comparison to their parent planets, often resembling captured asteroids. In contrast, the Moon is extraordinarily large relative to Earth, giving the pair a near-binary character, almost as if they form a double planet. The fact that it is large in diameter but light in mass only adds to its uniqueness. This oddity has long fascinated astronomers, and it continues to serve as a key to understanding planetary formation on a broader scale. By studying the Earth-Moon system, scientists gain insights into how impacts, accretion, and orbital dynamics shape celestial bodies across the solar system and beyond. Culturally, the difference between size and mass has also captured human imagination, though often indirectly. From Earth, the Moon appears immense, dominating the night sky with a presence that feels much greater than its true weight might suggest. Poets and dreamers have marveled at its fullness and brightness, while explorers who stood upon its surface discovered firsthand how its lightness changed movement and perception. The reduced gravity gave them a new kind of freedom, a way of bounding across the surface that no one had ever experienced before. The Moon's lightness, compared to its size, becomes not just a scientific observation but also a human experience, shaping how we connect emotionally with this constant companion. Ultimately, the fact that the Moon is 1/4 the size of Earth but has only 1/80th its mass is not just a statistic. It is a window into the history of both worlds, a key to understanding why the Moon looks and behaves as it does, and a reminder of the delicate balance that shapes our planet's environment. It tells of a past collision, of differing compositions, and of a gravitational relationship that has persisted for billions of years. The Moon's presence is both ordinary and extraordinary, and in its lightness compared to Earth's heaviness lies a story of cosmic origins, environmental consequences, and the enduring wonder that continues to draw our gaze skyward. About 4.5 billion years ago, when the solar system was still in its infancy and the planets were only beginning to take shape, a violent event occurred that would forever change the destiny of Earth and shape the sky we know today. In those early days, the young Earth was still molten, its surface a turbulent ocean of magma, bombarded constantly by debris left over from the formation of the Sun and the planets. Among the countless bodies orbiting the newborn Sun was a protoplanet roughly the size of Mars. Scientists call it Theia. It followed an unstable path that eventually brought it on a catastrophic collision course with Earth. When Theia finally struck, the impact was unimaginably powerful. It was not a gentle merging but a cosmic explosion, releasing more energy than any event humanity could ever witness. The collision tore away a significant portion of Earth's outer layers, sending vast amounts of molten rock and vaporized material into orbit around the planet. For a time, Earth was surrounded by a glowing ring of debris, a fiery halo circling the young world like a crown of chaos. Out of that ring, gravity began its slow and patient work. Over thousands of years, perhaps less, the scattered pieces started clumping together, drawn by their mutual pull, forming larger and larger bodies. Eventually, they coalesced into a single sphere. That sphere was the moon. This dramatic birth is known as the giant impact hypothesis, and while it is still a theory, it is supported by compelling evidence. The composition of lunar rocks brought back by Apollo astronauts is remarkably similar to that of Earth's mantle, suggesting a shared origin. Yet the moon is slightly depleted in volatile elements, just as one would expect from material that was once superheated and blasted into space by a massive collision. Even its orbit and size fit this story, as no other known mechanism explains how such a large satellite could have formed so close to Earth. The moon's formation changed our planet in profound ways. In the aftermath of the impact, Earth's rotation sped up, and the moon began orbiting at a much closer distance than it is today. Its gravitational pull exerted powerful tides on the young Earth, shaping its oceans and perhaps even influencing the early conditions that led to life. Over billions of years, the interaction between Earth and the moon has slowed Earth's rotation to its present pace and pushed the moon farther away, about 3.8 centimeters per year, a process still happening right now. Beyond these physical effects, the moon stabilized Earth's axial tilt, which controls the rhythm of the seasons. Without it, our planet's tilt might have wobbled chaotically over time, causing wild climatic swings that could have made the development of complex life far more difficult. The moon's silent presence has therefore been a guardian of stability, its pull gently moderating the Earth's behavior and nurturing the conditions that allowed life to flourish. For humanity, the moon has been more than just a companion in space. It has been a source of wonder, myth, and exploration. Long before we understood its origins, ancient peoples told stories about how it came to be. A lantern of the night, a deity, a symbol of cycles and change. Yet the real story is even more astonishing than any myth. It is the story of violence and creation, of destruction giving rise to beauty. From the chaos of a cataclysmic impact emerged the serene orb that now lights our nights. Every time we look up at the moon, we are gazing at a relic of that ancient event, a fragment of Earth itself reborn in the heavens. It is a reminder of our planet's turbulent youth and of the cosmic forces that shaped the world we live in. Its surface, scarred by billions of years of impacts, is like a time capsule preserving the story of the early solar system. And though it was born from chaos, it has become a symbol of constancy, rising and setting with unwavering regularity, marking the passage of time since those violent beginnings 4.5 billion years ago. The moon, though so close to Earth and so familiar in our skies, is a world profoundly different from our own. And one of the most striking differences is that it has no breathable atmosphere. To the naked eye, the moon seems to glow with life and presence, but in reality, it is a silent, airless sphere. On Earth, the atmosphere is not only a blanket of gases, but also the very medium that sustains life, providing oxygen to breathe, protecting the surface from harmful radiation, and moderating temperatures. The moon lacks all of these things, and this absence defines both its stark landscape and its inhospitable conditions. The reason the moon has no atmosphere lies largely in its size and gravity. With only about 1/6 the surface gravity of Earth, the moon is unable to hold onto gases that might otherwise form a protective layer. Any molecules of oxygen, nitrogen, or water vapor that might have once been present would have drifted away into space over time. Without a strong magnetic field to shield it, solar winds from the sun also sweep away particles that could gather around it. As a result, The moon cannot sustain the kind of thick, stable atmosphere that surrounds Earth. Instead, it possesses only an extremely thin exosphere made up of trace amounts of helium, argon, and other elements. This exosphere is so tenuous that its particles rarely collide with each other, making it more a near vacuum than anything resembling air. The lack of a breathable atmosphere has profound consequences for the moon's surface. Without air to scatter sunlight, the sky above the moon is not blue but pitch black, even in the middle of the day. Stars can be seen clearly, unshaken by atmospheric distortion, but the sun glares unfiltered and dangerous. There is also no protective shield against space debris. Meteoroids that would burn up in Earth's atmosphere strike the moon directly, pockmarking it with craters that remain for millions of years because there is no wind or rain to erode them. The landscape is therefore frozen in time, a record of impacts preserved in dust and rock. Another consequence of the lack of atmosphere is the extreme variation in temperature. On Earth, the air acts as a buffer, distributing heat and softening the contrast between day and night. On the moon, by contrast, temperatures swing violently. In the sunlight, the surface can heat up to over 100 degrees Celsius, while in the darkness of night it can plunge below -170 degrees. These brutal extremes make the moon a challenging place for human exploration and an impossible place for life as we know it to exist unaided. The absence of air also changes the very experience of being on the moon. There is no sound carried through the vacuum. The footsteps of astronauts and the movements of rovers are silent, except for what can be heard through radios inside their helmets. Dust stirred by movement falls quickly back to the ground without being carried by wind. The entire world is still and quiet, creating an eerie, otherworldly environment unlike anything on Earth. Yet this lack of atmosphere, while forbidding, has also provided scientists with unique opportunities. Because there is no weather or erosion, the moon's surface preserves the history of the solar system in its rocks and craters, offering clues about impacts and cosmic events that have long since been erased on Earth. The absence of atmospheric interference also makes the far side of the moon an ideal location for radio telescopes, shielded from Earth's signals and able to listen to faint whispers from the universe. For humans, however, the lack of breathable atmosphere remains the greatest challenge to living and working on the moon. Astronauts must carry their own supply of oxygen, wear protective suits, and shelter in habitats that replicate the pressure and air of Earth. Any vision of a future lunar base depends on technology to create artificial environments, using either imported supplies or resources extracted from the moon itself, such as oxygen bound in lunar rocks. The fact that the moon has no breathable atmosphere underscores just how rare and precious Earth's environment is. It highlights the uniqueness of our planet as a cradle of life, protected and sustained by a fragile but vital blanket of air. The moon, though beautiful and inspiring, is a reminder that not every world is hospitable. Its airless silence tells a story of isolation, of a companion that circles Earth without sharing its gift of life, and of the challenges humanity must overcome to reach beyond its home. On the moon, silence is absolute. Unlike Earth, where the air is constantly alive with sound, the moon has no atmosphere to carry vibrations. Sound, as it is experienced on our planet, is the product of waves moving through a medium such as air, water, or even solid matter. Without such a medium, those waves cannot travel. The moon's environment is a vacuum, and in that emptiness, noise does not exist. It is a world where even the loudest explosion would unfold in perfect quiet, and where the crunch of a boot in the dust makes no sound at all, except inside the helmet of the astronaut who makes it. This silence is not just a curiosity but a defining characteristic of the lunar experience. When astronauts from the Apollo missions set foot on the moon, they discovered firsthand that the environment was eerily still. On Earth, even in the quietest deserts or mountaintops, there are always sounds: the whisper of wind, the call of animals, the rustle of leaves. On the moon, none of these exist. The only noises astronauts could hear were those created within their suits: the hum of life support systems, the rush of circulating air, their own breathing, and the voices of colleagues speaking through radios. Communication depended entirely on radio waves transmitted electronically, for there was no way to shout across the lunar surface and be heard. The absence of sound changes the way events unfold on the moon. When a meteorite strikes its surface, for example, the impact may release enormous energy, throwing up dust and creating a crater, but no roar or crack accompanies the event in the vacuum of space. The same is true of equipment movements or even the firing of thrusters from a lander. Dramatic events that on Earth would be thunderous are, on the moon, carried out in silence. For astronauts, this added to the sense of otherworldliness, reinforcing the impression that they were not only far from home but also in a place where the normal rules of experience no longer applied. Though there is no sound in the lunar environment, vibrations can still be transmitted through solid material. An astronaut tapping on the side of a lander could feel the vibration through their glove, and seismometers placed on the surface during the Apollo missions recorded moonquakes caused by tidal forces or meteorite impacts. But these vibrations are not sound in the human sense. They remain silent unless converted into data or translated through equipment. For anyone standing on the surface, the moon itself does not speak. The silence has profound psychological and symbolic implications. On Earth, sound is one of the primary ways humans connect with their surroundings. The lack of it on the moon creates a sense of isolation, emphasizing the distance from home and the alien nature of the environment. Some astronauts describe this silence as awe-inspiring, a reminder of the starkness and purity of the lunar world. Others found it unsettling, as though something essential to life was missing. Yet for all, it underscored the fragility of human presence in such a place, where survival depended on technology and the thin bubble of air carried from Earth. This silence also makes the moon a unique place for science. Because there is no atmosphere to carry or distort sound, and no human noise pollution, the lunar far side is one of the quietest places in the solar system in terms of electromagnetic interference. Scientists have imagined placing radio telescopes there to listen to the faintest signals from the universe, undisturbed by the chatter of Earth's technology. The moon's natural silence, then, is not only a limitation but also an opportunity, turning it into a platform for exploration and discovery. That there is no sound on the moon is more than a scientific fact. It is part of what makes the lunar experience so haunting. The silence embodies the nature of space itself. Vast, empty, indifferent, and quiet. It is a silence that magnifies both beauty and loneliness, a reminder that Earth, with its endless chorus of waves, wind, voices, and life, is a rare and precious world. To step onto the moon is to step into that silence, to feel the absence of sound as much as the absence of air, and to know in the most immediate way how different and fragile human existence is beyond our planet. The discovery that water ice exists on the moon has transformed our understanding of Earth's closest neighbor and reshaped the possibilities for future exploration. For centuries, the moon was thought to be utterly dry, a barren sphere of rock and dust without any of the resources needed to support life or human presence. Telescopic observations showed no seas or rivers, and the harsh conditions, lack of atmosphere, extreme temperature swings, and relentless solar radiation, seemed to rule out the survival of water in any form. Yet in recent decades, evidence has revealed that water ice does, in fact, exist on the moon, hiding in its coldest and darkest regions. This discovery has turned the moon from a lifeless desert into a place of potential, not only for science but also for human settlement. The water ice is found primarily in permanently shadowed craters near the lunar poles. Because the moon's axis is only slightly tilted, some craters at its poles never receive direct sunlight. Temperatures in these regions can plunge below -170 degrees Celsius, cold enough to trap and preserve water molecules for billions of years. In these dark, cold traps, water delivered by comets, asteroids, or perhaps even volcanic activity on the moon itself has accumulated and remained stable, locked in ice. Remote sensing instruments aboard spacecraft such as NASA's Lunar Prospector, India's Chandrayaan-1, and NASA's Lunar Reconnaissance Orbiter detected the chemical signatures of hydrogen, strongly suggesting the presence of water. Later, more direct measurements confirmed patches of ice in these shadowed areas, a finding that once seemed improbable. The significance of lunar water ice extends far beyond its scientific novelty. Water is one of the most valuable resources for any form of life or long-term human activity. For astronauts, it could provide drinking water and oxygen through chemical separation. Even more importantly, water can be broken down into hydrogen and oxygen, the very components of rocket fuel. If humans can extract and use lunar ice, the moon could become a refueling station for deeper space missions, lowering the cost and difficulty of traveling to Mars or beyond. What once seemed a barren wasteland might instead become a vital outpost in humanity's expansion into the solar system. Scientifically, the presence of water ice also raises profound questions about the moon's history. Where did it come from? Was it deposited by comets and asteroids over billions of years? Or did volcanic eruptions on the young moon release water vapor that later froze in polar craters? The answers to these questions could provide insights into the early solar system and even the processes that delivered water to Earth. By studying the ice, scientists may gain clues about how habitable environments developed on our planet and elsewhere. At the same time, accessing this ice is not simple. The areas where it exists are some of the most difficult to reach. Permanently shadowed craters are not only cold but also dark, making exploration a technological challenge. Any future mission hoping to extract ice must deal with these extremes, as well as the difficulty of mining and processing ice mixed with lunar soil. Nevertheless, the potential rewards are so great that these challenges are seen as worth the effort. Plans for upcoming missions, both robotic and crewed, include studying these polar regions more closely, testing methods to extract water, and laying the groundwork for long-term use. For humanity, the discovery of water ice on the moon is not just a scientific detail. It is a symbol of possibility. It shows that even in places once assumed to be lifeless and barren, resources can exist that reshape our vision of the future. The moon, long regarded as a distant and sterile companion, now appears as a place that might sustain human activity, a stepping stone into the wider universe. The fact that water ice exists on the moon reminds us that exploration often overturns assumptions, revealing opportunities where none were imagined, and offering hope that the cosmos may be more hospitable than it first appears. The moon, though close to Earth and often bathed in its reflected light, is a world of extremes, especially when it comes to temperature. Unlike Earth, which has an atmosphere that acts as a blanket, trapping and distributing heat, the Moon has no such protection. Its thin exosphere is so tenuous that it cannot moderate temperatures or shield the surface from the full force of the Sun's rays. As a result, the lunar surface experiences some of the most dramatic temperature swings in the solar system, ranging from scorching heat to bitter cold depending on whether it is day or night. During the lunar day, when the sun shines directly on the surface, temperatures can soar to more than 120 degrees Celsius. This is hotter than boiling water, hot enough to make metal expand and electronics fail if they are not carefully designed to withstand such conditions. The heat is relentless because, without an atmosphere to scatter light or create weather, the sun's energy strikes the ground directly, baking the soil and rocks. To astronauts, the sun above the Moon appears harsh and unfiltered against a pitch-black sky, and the light reflects off the pale dust with blinding intensity. Equipment left in the sun must be shielded or insulated, otherwise it risks overheating in a matter of minutes. When the sun sets, however, the situation reverses completely. Without air to hold onto the heat absorbed during the day, the surface cools rapidly. In the darkness of lunar night, temperatures plunge to about -170 degrees Celsius, colder than the harshest winters on Earth. This cold is not just uncomfortable. It can freeze machinery, make materials brittle, and render survival impossible without advanced technology. The lunar night lasts about 14 Earth days, meaning any system left on the surface must endure 2 weeks of deep freeze. These conditions pose enormous challenges for building long-term habitats or leaving equipment behind. Even within a single day, the extremes can vary dramatically depending on location. Near the equator, where the sun strikes most directly, the heat is greatest, while at higher latitudes the temperature changes are somewhat less severe but still extreme by earthly standards. The most remarkable conditions are found at the poles. In some areas of permanent shadow, such as the depths of craters that never see sunlight, temperatures can fall even lower than -200 degrees Celsius. These cold traps are among the coldest places in the solar system, rivaling the frigid environment of Pluto, and yet it is precisely in these regions that water ice has been found, preserved for billions of years by the intense cold. The lack of atmosphere not only creates these temperature extremes but also changes the way heat moves across the surface. On Earth, winds and convection spread warmth, but on the Moon, heat can only transfer by radiation or conduction through solid rock. This means that shadows are sharp and unforgiving. A rock in sunlight may be searingly hot, while just centimeters away in shadow it could be freezing cold. For astronauts, this created unusual challenges, as their suits had to regulate body temperature against both extremes. Reflective layers, insulation, and liquid cooling systems became essential, ensuring they neither overheated in the sun nor froze in the shade. The extreme temperatures of the Moon also make it a testing ground for future exploration. Any permanent human presence will require habitats with strong insulation, energy storage systems to endure the long nights, and methods to protect machinery from both heat and cold. Engineers designing lunar bases must consider not only how to survive but how to thrive in a place where the environment swings from boiling hot to freezing cold with no gentle middle ground. Solar power, for example, works well during the day but becomes useless at night, forcing reliance on batteries or nuclear energy to survive the long darkness. These extremes remind us how special Earth truly is. Our atmosphere, our oceans, and our climate systems work together to create a habitable environment that smooths out the sun's heat and protects life. On the Moon, stripped of such protection, the raw reality of space is fully exposed. To step onto its surface is to confront an alien harshness, where survival depends entirely on preparation and technology. The moon's brutal temperatures are both a challenge and a lesson, showing us the fragility of life and the resilience required to explore beyond the shelter of our home planet. The moon, though long thought of as a still and silent world, is not entirely without activity. Just as Earth experiences earthquakes, the moon has its own form of seismic disturbances known as moonquakes. These quakes were first detected during the Apollo missions, when astronauts placed seismometers on the lunar surface to measure vibrations. What these instruments revealed surprised scientists. The moon, though far less geologically active than Earth, still trembles from time to time. These quakes tell us much about the nature of the moon's interior and about the differences between our planet and its closest companion. Unlike earthquakes, which are often caused by the movement of tectonic plates, moonquakes arise from several distinct sources. Some are shallow quakes that occur only a few kilometers beneath the surface and are among the strongest, sometimes registering up to 5 on the Richter scale. These can last for long periods, even close to an hour, because the moon's crust is dry and rigid, allowing seismic waves to travel with little damping. Others are deep quakes, occurring hundreds of kilometers below the surface, thought to be triggered by tidal forces as the Earth's gravity pulls on the moon. There are also thermal quakes, caused by the extreme temperature changes on the surface when the lunar night ends and the ground rapidly heats under the sun. Finally, meteorite impacts create sudden bursts of seismic activity, as rocks from space crash into the moon without an atmosphere to slow them down. The existence of moonquakes has profound implications. They suggest that the moon is not a completely dead world, but one that still responds to stresses and forces. While it lacks the plate tectonics that shape Earth's surface, the moon's interior still holds energy that can be released in sudden movements. This makes the moon's geology more complex than the image of a frozen, unchanging sphere that once dominated scientific thought. The persistence of seismic activity, billions of years after the moon's formation, provides clues about its inner structure and how it has cooled over time. One striking difference between moonquakes and earthquakes is the way the vibrations behave. On Earth, water in the crust and mantle absorbs and dissipates much of the energy, which is why quakes usually subside relatively quickly. On the moon, the lack of water means that seismic waves echo back and forth inside the rigid crust, making the ground shake for much longer. Apollo seismometers recorded some quakes reverberating for nearly an hour, a phenomenon scientists described as the moon ringing like a bell. This unusual behavior highlights just how dry and brittle the moon's body is compared to Earth's dynamic interior. For future lunar exploration, moonquakes represent both a challenge and an opportunity. The strongest shallow quakes, though infrequent, could pose a risk to structures built on the moon's surface. Habitats, instruments, and equipment will need to be designed to withstand long-lasting tremors in an environment already filled with other hazards like extreme temperatures and abrasive dust. At the same time, the data from moonquakes are invaluable for mapping the moon's interior. Just as earthquakes help geologists understand Earth's layers, moonquakes reveal the composition and depth of the lunar crust, mantle, and core. Through seismic studies, scientists have learned that the moon has a small, partially molten core and a mantle that is cooler and less active than Earth's, but still capable of producing seismic events. The discovery of moonquakes has also changed the way we view the moon in a broader sense. Rather than being a static relic, it is a body that continues to interact with its environment, shaped by gravity, temperature, and impacts from space. Its tremors connect it to Earth. As the pull of our planet contributes to its seismic activity, reminding us of the dynamic relationship between the two worlds. That the moon has quakes is a fact that deepens its mystery and significance. It shows that even in the silence of space, beneath the dusty surface of a seemingly lifeless world, there is hidden movement and energy. These subtle but persistent tremors are the heartbeat of the moon, a sign that it is not entirely still but continues to live in its own quiet, alien way. The moon may seem like a permanent fixture in the night sky, always the same distance from Earth, rising and setting with unchanging regularity. Yet in reality, it is slowly slipping away. With each passing year, the moon drifts about 3.8 centimeters farther from Earth, roughly the rate at which human fingernails grow. Though the change is imperceptible on human timescales, over millions and billions of years it becomes profound, reshaping the relationship between our planet and its only natural satellite. This gradual separation is the result of a subtle but powerful interaction between Earth and the moon known as tidal forces. As the moon orbits Earth, its gravity pulls on our planet, raising tides in the oceans and even slight bulges in the solid crust. But Earth rotates much faster than the moon orbits, once every 24 hours compared to the moon's orbit of about 27.3 days. So these tidal bulges do not line up directly beneath the moon. Instead, they are dragged slightly ahead by Earth's faster rotation. The offset bulges exert a forward pull on the moon, giving it a tiny boost in speed. According to the laws of orbital mechanics, when an orbiting object gains speed, it moves outward to a higher orbit. So, as the moon is tugged forward, it slowly spirals away from Earth. At the same time, Earth pays a price for this exchange of energy. Its rotation gradually slows down. This is why days on Earth are becoming longer, albeit by only a fraction of a second per century. In the distant past, days were much shorter, about 18 hours long some 1.4 billion years ago, and the moon was significantly closer, looming larger in the sky and exerting even stronger tides. We know this drift is happening thanks to an experiment left on the moon more than half a century ago. During the Apollo missions, astronauts placed arrays of mirrors, called retroreflectors, on the lunar surface. By bouncing laser beams off these mirrors and timing how long the light takes to return, scientists can measure the moon's distance from Earth with remarkable precision, down to the millimeter. These measurements show clearly that the moon is receding at a steady pace, confirming predictions made by theories of tidal evolution. The consequences of this slow departure reach far into the future. As the moon moves farther away, Earth's rotation will continue to slow, and the length of a day will keep increasing. Eventually, the system will reach a point where Earth's rotation matches the moon's orbital period. When that happens, Earth will always show the same face to the moon, just as the moon already shows the same face to us. However, this state of mutual tidal locking is billions of years away, and long before it occurs, other cosmic changes, such as the sun's transformation into a red giant, will likely reshape the Earth-Moon system entirely. The moon's gradual retreat also affects the tides, though the change is so slow that it is noticeable only over immense spans of time. As the moon recedes, its gravitational pull on Earth weakens, and tides become less extreme. This gentle decline could influence the long-term evolution of Earth's climate and ecosystems, which have been shaped in part by the ebb and flow of the tides over geological time. Looking back, the moon's closeness in Earth's youth had dramatic effects. Its stronger pull not only raised higher tides, but also may have influenced the behavior of early life in the shallow seas, where tidal cycles created constantly changing environments. The slowing of Earth's rotation, driven by the moon's pull, also helped stabilize our planet's axial tilt, keeping the seasons relatively stable, a crucial factor in the development and persistence of complex life. There is something poetic about this slow separation. The Moon, born from Earth's own material in a violent collision over 4.5 billion years ago, has been a constant companion ever since, shaping our world in countless ways. Yet it is gradually moving on, drifting farther into space, centimeter by centimeter, year after year. The bond is not broken. Gravity ensures that the two will remain linked for eons, but the distance grows. When we look up at the Moon today, we see it as humans have for all of history, but it is not quite where it once was. Long ago, it shone larger and brighter. Far in the future, it will appear slightly smaller, though still bound to Earth's side. Its slow departure is a reminder that even seemingly eternal relationships in the cosmos are dynamic, always changing. The Moon's journey outward is a quiet, ongoing story written in the language of gravity and time, a story that began in fire and chaos and continues, millimeter by millimeter, into the farthest future. A day on the Moon is nothing like a day on Earth. While we measure our days in hours, 24 of them from one sunrise to the next, the Moon's day stretches across weeks. One full lunar day, the time it takes for the Moon to rotate once on its axis and return to the same position relative to the Sun, lasts about 29.5 Earth days. That means that if you were standing on the Moon, you would see the Sun rise slowly over the horizon, climb high into the black sky, and then sink again, all over the course of nearly an entire month on Earth. Daylight would last for about 2 weeks, followed by roughly 2 weeks of darkness, as night settled across the lunar surface. This long lunar day is the result of a cosmic dance between Earth and its satellite. The Moon is tidally locked to Earth, which means it rotates on its axis at the same rate that it orbits our planet. Because of this, the same side of the Moon always faces us, a familiar face we have watched for millennia. But while tidal locking keeps one hemisphere turned toward Earth, the Moon still rotates, just very slowly, completes one rotation in about 27.3 Earth days, which is the same amount of time it takes to orbit Earth once. However, because Earth itself is moving around the Sun during that period, the Moon must rotate a little more before the Sun appears in the same place in its lunar sky. That extra motion stretches a lunar solar day, sunrise, to about 29.5 Earth days. The slow rhythm of lunar time creates an environment unlike anything we experience here. During the long lunar day, sunlight pours down without pause for about 14 Earth days. With no atmosphere to scatter light or regulate temperature, the surface is exposed directly to the Sun's unfiltered radiation. Temperatures soar to around 127 degrees Celsius, hot enough to boil water in an instant. Shadows are stark and black, and the sky remains a deep, star-studded darkness even at noon, because there is no air to scatter the sunlight into a blue glow as it does on Earth. Then, just as slowly as it came, the Sun dips below the jagged horizon, and night takes hold, not for hours but for another 14 Earth days. Without sunlight, the lunar surface radiates its heat into space, cooling rapidly. Temperatures plunge to around minus 173 degrees Celsius, colder than any natural temperature found on Earth. The landscape lies in darkness, illuminated only by the distant stars and the faint reflected light of Earth. For half a month, the Moon sleeps in the cold silence of space before the Sun returns to begin the cycle again. This extreme day-night pattern poses enormous challenges for exploration. Lunar missions must be carefully timed to land and operate during the 2-week-long day when solar power is available. Surviving the bitter cold of the lunar night requires advanced engineering and energy storage solutions. Future lunar bases will have to be designed with these rhythms in mind, providing insulation and power systems that can endure the long stretches of darkness and heat. Yet, these long days also reveal the moon's nature as a world governed by cosmic harmony. Its slow rotation and synchronized orbit are not accidents but the result of billions of years of gravitational interaction with Earth. Over time, tidal forces drained the moon's rotational energy, slowing its spin until one side locked toward Earth. What was once perhaps a faster spinning body became a steady companion, turning just enough to keep pace with its orbit. For humans looking up from Earth, this cycle is reflected in the phases of the moon, new, crescent, quarter, full, a 29.5-day pattern that mirrors the length of a lunar day. It shapes calendars, tides, and traditions, weaving itself into the fabric of human culture. And though we think of a day as something ordinary, on the moon it is a grand, slow procession, a reminder of the vast scales on which the universe operates. Every lunar sunrise is a rare event, and every sunset marks the beginning of a long night in the silence of space. To stand on the moon and watch that sky change would be to feel time itself stretch and slow, moving not in hours but in weeks, as the ancient rhythms of the cosmos unfold above a silent, airless world. Among all the moons that circle the planets of our solar system, and there are more than 200 of them, Earth's moon holds a special distinction. It is not the largest moon outright. That title belongs to Ganymede, orbiting Jupiter. But when measured relative to the size of its planet, our moon is the largest by far. It is about 1/4 the diameter of Earth and roughly 1/80th of its mass. No other natural satellite comes close to this proportion. Most moons are tiny in comparison to the worlds they orbit, but the moon is so large relative to Earth that the two are sometimes described as a double planet system rather than a planet and its satellite. This unusual size is no coincidence. It is a clue to the moon's dramatic origin. Scientists believe that more than 4.5 billion years ago, not long after Earth itself formed, a Mars-sized protoplanet named Theia collided with the young Earth. The impact was cataclysmic, blasting vast amounts of molten rock and debris into orbit. Over time, that material coalesced under the pull of gravity to form the moon. Because it was born from Earth's own mantle, the new satellite was much larger, relative to its parent planet, than most moons that formed by simple capture or co-accretion. The result was a world that, though smaller and airless, remained closely tied to Earth, a companion shaped from the same ancient collision. The moon's exceptional size has profound consequences. Its gravitational influence is strong enough to stabilize Earth's axial tilt, keeping our seasons relatively steady over millions of years. Without this stabilization, Earth's tilt might wobble wildly, causing dramatic climate shifts that could have hindered the development of life. The moon also drives the rise and fall of tides, shaping coastal ecosystems and influencing the rhythms of countless species, including humans. Its large size is what gives it this powerful gravitational pull. A smaller satellite would exert far weaker effects. No other planet-moon pair in the solar system shows such a close match in size. Jupiter and Saturn, the giants of the solar system, each host dozens of moons, but even their largest satellites, Ganymede and Titan, are only tiny fractions of their planet's size. Mars has 2 small moons, Phobos and Deimos, which are little more than captured asteroids. Neptune's moon Triton is relatively large, but still far smaller in proportion to Neptune than our moon is to Earth. Even Pluto, which has a moon called Charon almost half its size, exists in a different category, since Pluto itself is no longer classified as a full-fledged planet. Among the 8 recognized planets, Earth and its moon stand alone in their unusual size ratio. This unusual balance also affects how the Earth-Moon system moves through space. The gravitational tug between the two bodies is so significant that they do not orbit strictly around Earth's center, but rather around a shared center of mass, known as the barycenter. This point lies about 4,700 kilometers from Earth's center, roughly 3/4 of the way to the surface, meaning the Moon's influence literally shifts Earth as they both circle the Sun together. In this sense, Earth and the Moon behave more like a binary system than a typical planet and satellite pair. The Moon's size also shaped its own evolution. Its gravity was strong enough to maintain volcanic activity in its youth, forming vast basalt plains called maria. It retained enough mass to become nearly spherical, unlike many small, irregular moons elsewhere in the solar system. And its presence so close to Earth made it an accessible destination for exploration, the only world beyond our own where humans have set foot. Because of its unusual size, the Moon has been a defining feature of Earth's story from the very beginning. It influences our tides, our seasons, even the length of our day, which has gradually increased as tidal forces slow Earth's rotation. It has guided human calendars and inspired myths in every culture. And it continues to shape the planet's environment in ways subtle and profound. When we look up at the night sky and see the Moon's familiar face, we are not merely seeing a small companion circling a large planet. We are witnessing one half of a remarkable partnership, a satellite so large and significant that it blurs the boundary between Moon and planet. In the vast diversity of the solar system, Earth's Moon is unique, not for its absolute size but for the extraordinary proportion it shares with its world, a silent reminder of the ancient collision that bound them together and the deep, gravitational bond that continues to shape them both. A lunar eclipse is one of the most striking and beautiful events visible in the night sky, a phenomenon that occurs when the Earth passes directly between the Sun and the Moon, casting its shadow across the lunar surface. Unlike the everyday phases of the Moon, which are caused by its changing position relative to the Sun and Earth, an eclipse is a rarer alignment, a moment when the three celestial bodies line up in near-perfect geometry. To those who watch from Earth, the familiar silver-white Moon transforms into something extraordinary, often glowing with deep shades of red or copper as it slips into the planet's shadow. The mechanics of a lunar eclipse are straightforward yet awe-inspiring. As the Earth blocks sunlight from reaching the Moon, its shadow falls across the lunar surface. Because Earth's atmosphere bends and scatters some of the Sun's light, particularly the redder wavelengths, a dim glow reaches the Moon even during totality. This is why the Moon does not disappear completely, but instead takes on the eerie, reddish hue often called a blood moon. The exact color depends on conditions in Earth's atmosphere at the time. Dust, clouds, or volcanic ash can make the Moon appear darker or more intensely red. There are different types of lunar eclipses, depending on how deeply the Moon passes into Earth's shadow. In a penumbral eclipse, the Moon only enters the outer, lighter part of the shadow, causing subtle dimming that is often hard to notice. In a partial eclipse, a portion of the Moon is clearly darkened as it moves into the inner, umbral shadow. The most dramatic is a total eclipse, when the entire Moon is engulfed in Earth's umbra, creating the striking blood-red disk that has captured human imagination for millennia. Each type offers its own unique beauty, though total eclipses remain the most memorable for casual observers. Lunar eclipses are visible to anyone on the night side of Earth when they occur, unlike solar eclipses, which are only visible along a narrow path. This makes them more accessible, and historically they have been widely observed across cultures. Ancient peoples often regarded them with a mix of awe and fear, interpreting the sudden darkening of the moon as a supernatural sign. Some believed it was being swallowed by mythical creatures, while others saw it as an omen of change, conflict, or divine intervention. Over time, as astronomy advanced, people came to understand the natural explanation, but the sense of wonder has never disappeared. For scientists, eclipses have long been valuable opportunities to study both the moon and Earth. Observations of Earth's curved shadow across the lunar surface provided some of the earliest evidence that our planet is round. During eclipses, astronomers can also analyze the faint sunlight that passes through Earth's atmosphere and reflects off the moon, offering insights into the composition of the atmosphere itself. This same principle is now applied in modern astronomy to study the atmospheres of distant exoplanets, showing how something as familiar as a lunar eclipse can inspire techniques for exploring faraway worlds. For modern observers, lunar eclipses remain special because of their rarity and beauty. They occur only a few times each year, and not all are total. When one does happen, it often draws people outdoors late at night or in the early hours of morning, gathering in fields, backyards, or city rooftops to witness the celestial show. The experience is enhanced by its universality. Unlike meteor showers or solar eclipses that depend heavily on location, anyone under the darkened sky has the chance to watch. There is something unifying in the knowledge that millions of people across continents may be gazing at the same glowing red moon. A lunar eclipse is more than just a shadow crossing a celestial body. It is a reminder of the intricate dance of the Earth, moon, and Sunday. It reveals the elegance of celestial mechanics, the delicate alignments that occasionally transform the ordinary into the extraordinary. The eclipses of the moon remind us that even familiar objects can take on entirely new appearances when viewed from a different perspective, and that the cosmos still holds wonders visible to anyone who takes the time to look up. The first artificial impact on the moon was a milestone in human exploration of space, marking the moment when human-made technology reached beyond Earth and touched another world. This event took place on September 14, 1959, when the Soviet spacecraft Luna 2 collided with the lunar surface. Before this achievement, the moon had always been an untouchable sphere, studied from afar with telescopes and imagined through myths and stories. Luna 2 changed that forever, proving that humanity could send machines across space to make contact with a celestial body nearly 400,000 kilometers away. Luna 2 was launched at the height of the Cold War, during the early years of the space race between the Soviet Union and the United States. The two superpowers were striving to demonstrate technological superiority, and space became the ultimate stage on which their rivalry played out. Only 2 years earlier, the Soviet Union had shocked the world by launching Sputnik, the first artificial satellite, into Earth's orbit. Luna 2 built on that momentum, aiming not just to orbit Earth but to reach the moon itself, something that had never been done before. When the spacecraft completed its journey and struck the lunar surface, it gave the Soviets another victory in the early stages of space exploration. The spacecraft was designed as a spherical probe, packed with scientific instruments intended to measure cosmic rays, solar wind, and magnetic fields during its journey. Though its final act was to crash into the moon, the data it transmitted during its flight was of great importance to scientists. It confirmed, for example, that the moon had no detectable magnetic field and no significant radiation belts surrounding it. These findings, while perhaps less celebrated than the dramatic impact itself, were crucial pieces of information that deepened human understanding of the lunar environment. The impact occurred in the region near the Mare Imbrium, one of the large, dark plains visible from Earth. As Luna 2 struck the surface, it carried with it two metal spheres that bore the emblem of the Soviet Union. These symbolic tokens made it the first human-made object to rest on the moon, even though the landing was not gentle. For the Soviets, this was not only a scientific breakthrough but also a political statement. It demonstrated their capability to send spacecraft beyond Earth and gave them a propaganda victory in their competition with the United States. For the broader world, Luna 2 represented the opening of a new era. Humanity had for the first time extended its presence beyond Earth, not through human footsteps but through the technology humans had built. The idea that an object created on Earth could travel through space and physically touch the moon was revolutionary. It transformed the moon from a distant, untouchable light in the sky into a destination, a place that human ingenuity could reach. This breakthrough laid the foundation for all future missions, both robotic and crewed. The success of Luna 2 was soon followed by other missions, both Soviet and American, that attempted flybys, impacts, and eventually soft landings. Each step built on the confidence gained from that first impact. Without it, the later triumphs of Apollo and the human footsteps on the moon might have seemed far less attainable. Luna 2's crash was not the end of something but the beginning, a first contact that opened the way for exploration and discovery. Although more than 6 decades have passed since Luna 2 made its mark, its legacy remains significant. The spacecraft itself is gone, shattered into fragments on the moon's surface, but its symbolic weight endures. It stands as the first moment in history when Earth and Moon were connected by human effort, when technology crossed the gulf of space and touched another world. The first artificial impact on the moon was not a graceful arrival, but it was a decisive one, proving that humanity had taken its first step beyond Earth and into the wider cosmos. Humans have walked on the moon, and this fact remains one of the most extraordinary achievements in the history of our species. For thousands of years, the moon was a distant and untouchable companion in the night sky, inspiring myths, shaping calendars, and stirring the imagination of poets and dreamers. To ancient civilizations, it was a divine presence or a realm of mystery. For scientists of the modern age, it became an object to be studied and understood. Yet, for all its familiarity, the moon remained out of reach until the 20th century, when technology and determination combined to make the impossible possible. The first human steps on the moon were taken on July 20, 1969, during the Apollo 11 mission. After a journey of nearly 400,000 kilometers through space, astronauts Neil Armstrong and Buzz Aldrin descended from their lunar module, leaving behind the first footprints on another world. Armstrong's step was more than just a personal triumph or even a national achievement. It was a milestone for humanity as a whole, a moment when humans extended their presence beyond Earth for the first time. Millions watched the event on television, hearing Armstrong's famous words and realizing that the moon, once untouchable, now carried the marks of human exploration. Over the course of the Apollo program, 12 astronauts in total walked on the moon between 1969 and 1972. Each mission brought new discoveries and experiences. The explorers drove rovers across the surface, collected rocks, set up scientific instruments, and conducted experiments in conditions utterly unlike those of Earth. The samples they returned offered invaluable insight into the moon's origins, supporting theories that it was formed from debris after a colossal collision in Earth's early history. The data gathered from seismic equipment and other instruments revealed details about its structure, its composition, and its long, violent geological past. The human experience on the moon was not only scientific but also deeply emotional. astronauts spoke of the stark beauty of the lunar landscape, with its gray dust, towering craters, and stillness unlike anything on Earth. They described the strangeness of moving in low gravity, where each step became a bounding leap, and the challenge of performing delicate tasks while wearing bulky suits. Perhaps most profoundly, they reflected on the sight of Earth from the moon, a fragile, glowing sphere suspended in the blackness of space. These reflections changed perspectives not only for the astronauts themselves but also for those on Earth who saw the iconic photographs of our planet rising over the lunar horizon. The moon became a place of discovery, but it also became a mirror, showing humanity the beauty and fragility of its home world. Yet the era of human presence on the moon was short-lived. After Apollo 17 in 1972, no human has returned. Political priorities shifted, budgets were reduced, and the focus of space exploration turned elsewhere, toward orbital stations, robotic missions, and later Mars. Still, the legacy of those years endures. The footprints remain in the dust, untouched by wind or rain, a permanent reminder of what humans achieved. The technology developed for Apollo paved the way for new advances in science and engineering, and the inspiration it created continues to influence generations of scientists, engineers, and explorers. Today, more than 50 years later, the idea of humans on the moon is no longer a memory of the past but once again a vision for the future. Nations and private companies alike are planning new missions, aiming not just to visit but to stay, to build bases, and to use the moon as a stepping stone for journeys deeper into space. The fact that humans have already walked there shows that it is possible. The challenge now is not whether we can return, but how we will use the opportunity to expand our knowledge and our presence in the universe. That humans have stood on the moon is more than a historical footnote. It is a testament to curiosity, perseverance, and the drive to push beyond limits. It marks a moment when the boundary between Earth and sky was crossed, when imagination became reality. The story of humans on the moon is not finished. It is the opening chapter of a much larger journey outward into the cosmos. The moon plays a crucial role in shaping life on Earth through its influence on the tides. Although the moon is far away, nearly 384,400 kilometers from Earth, its gravitational pull is strong enough to tug at the planet's oceans, creating the rhythmic rise and fall of sea levels we know as tides. This effect is one of the most visible demonstrations of the moon's power over our world, a constant reminder that Earth and its satellite are bound together in a gravitational relationship that touches both land and sea. The process behind tides begins with the moon's gravity. As the moon pulls on Earth, it draws the water in the oceans slightly toward itself, creating a bulge of water on the side of Earth facing the moon. At the same time, because Earth itself is being pulled more strongly than the water on its far side, another bulge forms on the opposite side. This results in two tidal bulges around the globe. As Earth rotates on its axis, different regions pass through these bulges, experiencing high tide when aligned with them and low tide in between. The sun also plays a role in this process, but the moon's influence is stronger because of its proximity, making it the dominant force behind the daily cycle of tides. The regularity of tides has shaped human civilization for millennia. Coastal communities learned to observe and predict the rise and fall of the sea, using this knowledge for fishing, navigation, and trade. Harbors depended on tidal patterns, and entire economies were built around the rhythm of the ocean. In some regions, such as the Bay of Fundy in Canada, the tidal range is so dramatic that the difference between high and low tide can exceed 15 meters, transforming the landscape twice each day. Such extreme cases highlight the moon's ability to reshape the face of the Earth, not only through long-term geological forces but also through daily, observable cycles. Beyond human use, tides have been vital to the development of life itself. Some scientists believe that early tidal pools provided an environment where primitive organisms could evolve. These pools, alternately filled and drained by the tide, created natural laboratories of changing conditions that may have encouraged the development of more complex biological structures. Even today, intertidal zones, where land and sea meet and tides ebb and flow, are among the richest ecosystems on Earth. They support diverse species of plants and animals that have adapted to the constant rhythm of change, depending on the moon's pull for their survival. The moon's role in tides also extends to shaping Earth's stability. The tidal interaction between Earth and moon gradually transfers energy from our planet to its satellite, causing Earth's rotation to slow very slightly over long periods of time. At the same time, the moon slowly drifts away from Earth at a rate of about 4 centimeters per year. This interplay has helped stabilize Earth's axial tilt, which governs the seasons. Without the moon's steadying influence, Earth's climate might have swung wildly, making life far less predictable and perhaps less hospitable. The tides themselves have inspired awe and imagination. To ancient peoples, the rhythmic rising and falling of the ocean seemed like a sign of divine power or a message from the heavens. In many cultures, the moon was linked to fertility, cycles, and renewal, its connection to tides reinforcing its role as a symbol of rhythm and transformation. Even now, the sight of a full moon shining over an incoming tide carries a kind of poetry, reminding us of the intimate bond between sky and sea. Today, tides continue to be important not only for ecosystems and coastal communities, but also as a potential source of renewable energy. Engineers are developing tidal power systems that harness the movement of water to generate electricity, a clean and predictable form of energy made possible by the moon's constant gravitational pull. In this way, the moon's influence may help sustain humanity's future, just as it has shaped its past. The fact that the moon causes tides is more than a matter of physics. It is a connection that ties our planet's oceans to the sky, a force that has influenced nature, culture, and science alike. Each wave that rises and falls at the shore is a reminder of the silent pull of our companion in space, a testament to the enduring bond between Earth and Moon. When astronauts first brought moon rocks back to Earth during the Apollo missions, scientists were eager to examine them for clues about the moon's origin and its relationship to Earth. What they found was surprising and profound. Many of the rocks from the lunar surface are older than the oldest rocks ever discovered on Earth. This realization reshaped our understanding of both the moon and our own planet, offering insights into the violent and dynamic history of the early solar system. The oldest rocks found on Earth date back about 4.0 billion years, while some lunar rocks are more than 4.4 billion years old. This difference arises not because Earth formed later than the moon, but because Earth has remained geologically active. Our planet's crust is constantly recycled through processes like plate tectonics, volcanism, and erosion. Mountains rise and wear away, oceans shift, and new crust is formed while old crust is destroyed. As a result, much of Earth's earliest geological history has been erased or transformed beyond recognition. On the moon, however, no such processes exist. Without an atmosphere, without liquid water, and with only limited volcanic activity long ago, its surface preserves ancient rocks in a way Earth cannot. The moon is, in effect, a time capsule of the early solar system. The Great Age of Moon Rocks tells us that the moon formed shortly after the solar system itself began to take shape around 4.5 billion years ago. Most scientists support the giant impact hypothesis, which suggests that a Mars-sized body collided with the young Earth, blasting material into space that eventually coalesced into the Moon. The rocks confirm this story by revealing similarities in chemical composition between the Moon and Earth, while also showing evidence of having been melted and reshaped in a massive, cataclysmic event. Their great age means they record the immediate aftermath of this colossal collision, offering a glimpse into a chapter of history that Earth's active geology has long since erased. Studying the composition of these ancient rocks has revealed more than just their age. Many are rich in anorthosite, a light-colored rock that formed from the cooling of the Moon's original magma ocean. These minerals crystallized at the surface, floating upward and solidifying into the crust billions of years ago. The survival of such rocks gives scientists direct evidence of processes that shaped not only the Moon but also other rocky bodies in the solar system. In contrast, rocks of this kind on Earth have long since been transformed or destroyed. By holding Moon rocks in their hands, scientists have held fragments of a world that has remained nearly unchanged since the dawn of planetary history. The fact that lunar rocks are older than Earth's rocks also emphasizes the fragility of Earth's geological memory. Our planet is dynamic and life-sustaining precisely because it recycles itself, but this very dynamism erases much of its earliest record. The Moon, by preserving ancient rocks on its quiet, airless surface, fills in those missing chapters. Through its stones, we gain insights into the bombardment Earth and the Moon endured during the heavy impact period, when asteroids and comets rained down and may have delivered water and organic material essential for life. Without the Moon's ancient record, much of that history would remain a mystery. For astronauts who collected them, Moon rocks were not just scientific samples but tangible evidence of humanity's ability to reach beyond Earth. For scientists, they remain priceless treasures, still studied decades after they were first returned. Each fragment tells a story older than any found in Earth's crust, a reminder that the Moon has been a silent witness to the entire saga of life and change on our planet. That Moon rocks are older than Earth's rocks is more than a curious fact. It is a key to understanding how worlds form and evolve. In their silent, ancient grains, these stones carry the memory of creation itself, bridging the gap between Earth's forgotten past and the history written across the wider solar system. They remind us that sometimes we must look beyond our own world to truly understand it. The Moon, long seen as a barren and lifeless world of dust and rock, has revealed itself to be far more complex than early astronomers imagined. In the decades since humans first set foot on its surface, scientists have studied lunar samples with increasing precision, and one of the most fascinating discoveries is the presence of unusual minerals unlike many found on Earth. These minerals are not only rare but also carry within them the story of the Moon's violent birth, its fiery youth, and the cosmic events that have shaped it over billions of years. When Apollo astronauts brought back lunar rocks and soil in the late 1960s and early 1970s, scientists expected them to be composed mostly of familiar materials, and many were. Basalt, for example, formed from ancient volcanic eruptions, was abundant on the vast plains known as Maria. But mixed among the more common minerals were strange crystalline structures that had never been seen before. One of the most intriguing was armalcolite, named after Armstrong, Aldrin, and Collins, the crew of Apollo 11. This mineral was first identified in lunar samples before it was ever found on Earth, highlighting how different conditions on the Moon had created substances that do not commonly form here. Another discovery was tranquilityite, a dark, zirconium-rich mineral named after the Sea of Tranquility where Apollo 11 landed. Like armalcolite, it was first known only from the Moon, and its presence told scientists much about the Moon's volcanic history and the slow cooling of magma beneath its surface. These minerals crystallized under conditions quite unlike those on Earth, shaped by the moon's lower gravity, lack of atmosphere, and unique geologic evolution. They offered a window into processes that occurred more than 3 billion years ago, preserved in pristine form because the moon's surface has remained geologically inactive for most of its history. More recently, scientists have found even stranger materials hidden within lunar rocks. Among them are minerals that appear to be the result of asteroid impacts. Because the moon has no atmosphere to burn up incoming meteoroids, it is constantly bombarded by space debris. The immense heat and pressure from these collisions can melt rock and even form glass-like minerals that do not occur naturally on Earth's surface. Some of these impact-related minerals, such as spinel and masclenite, have revealed information about the intensity of ancient impacts and the composition of the bodies that struck the moon. Even more astonishing is the discovery of minerals thought to form only under extreme conditions deep within planetary interiors. Small grains of apatite found in lunar samples, for example, have provided evidence that the moon once contained far more water than scientists previously believed. Their composition suggests that volatile elements, including hydrogen, were present during the moon's formation, a clue that challenges older ideas of the moon as a completely dry body and reshapes theories about how it evolved. New lunar missions and advanced analytical techniques continue to deepen the mystery. Robotic probes and remote sensing instruments have detected unexpected mineral signatures in areas never sampled by humans, such as the moon's far side and its polar regions. Some of these minerals may have formed in the aftermath of massive impacts that melted and recrystallized the surface, while others may be remnants of the moon's primordial crust, fragments of a global magma ocean that once enveloped the young satellite shortly after its formation. These discoveries have broader implications beyond lunar geology. They offer clues about the history of the early solar system, when violent collisions and intense heat shaped the planets and their moons. By studying minerals that do not exist or are extremely rare on Earth, scientists gain insight into processes that occurred under conditions we cannot replicate here. They also hint at the possibility of valuable resources, such as rare metals or helium-3, that future explorers might one day mine for use on Earth or in space. Each unusual mineral found on the moon is like a page from an ancient record, preserving information about events billions of years old. Together, they reveal a world that is far from simple, a place forged in fire, shaped by impacts, and still holding secrets beneath its dusty surface. What once seemed a dead, unchanging sphere is now understood as a rich geological archive, its minerals telling the story of cosmic violence, volcanic fury, and the slow, patient work of time. As exploration continues, the moon's hidden treasures will keep rewriting what we know about its past, and, by extension, about the history of our own planet and the solar system we share. The surface of the moon is covered in a fine, powdery dust that gives it its gray and muted appearance, a layer known as regolith. At first glance, this dust might seem like an unimportant detail, but it is one of the most defining characteristics of the lunar environment. The dust covers nearly everything, coating rocks, filling craters, and softening the edges of the rugged landscape. It is not the kind of dust familiar on Earth, formed by organic particles or weathering driven by air and water. Instead, lunar dust is the product of billions of years of impacts from meteoroids, comets, and micrometeorites that have bombarded the moon's surface. With no atmosphere to burn up incoming particles, the moon has been struck countless times, each collision breaking rocks into smaller fragments and gradually grinding them into powder. The result is a layer of dust that varies in depth, from a few centimeters in some regions to several meters in others. This texture is both fascinating and troublesome. To astronauts who walked on the moon, it felt soft underfoot, almost like talcum powder, yet it was also sharp and clingy, made of tiny jagged grains of rock and glass. Because the moon has no weather to round off their edges, each grain remains rough and abrasive. This gave the dust an unusual ability to stick to everything it touched: spacesuits, equipment, and even the visors of helmets. Once tracked into the lunar module, the dust clung to fabric and irritated the astronauts' lungs when brushed off into the air, creating a challenge that had not been fully anticipated. Scientifically, the lunar dust holds great importance. Within it are fragments of rock and mineral that tell the story of the moon's geological history. Tiny glass beads formed in the heat of impacts, as well as particles fused by ancient volcanic eruptions, are mixed into this fine soil. Each grain is like a tiny record of violent events and slow changes over billions of years. By studying the dust brought back from Apollo missions, scientists have learned not only about the moon's surface but also about the broader history of the solar system, since many of the impacting bodies that created it were remnants of the system's earliest formation. The dusty surface also affects the appearance of the moon as we see it from Earth. The way sunlight reflects off this fine layer gives the moon its distinctive brightness and its ability to shine so strongly in the night sky. The regolith's reflective properties also make certain regions appear lighter or darker, contributing to the contrast between the highlands and the Maria that form the patterns humans have long imagined as faces or figures on the moon. Yet the dust is more than just a scientific curiosity or a visual feature. It represents one of the greatest challenges for future lunar exploration. Because of its abrasive nature, it can wear down machinery, scratch visors, and interfere with seals and joints. Astronauts during the Apollo missions reported that it wore into their suits and caused mechanical issues when it got into hinges and moving parts. For longer stays on the moon, dealing with this dust will be essential. Engineers are working on technologies such as dust-resistant materials, electrostatic repulsion systems, and better filtration to ensure that future explorers can live and work safely despite the ever-present powder. At the same time, the dust may also prove to be a valuable resource. Within the regolith are oxygen atoms bound in minerals, which could potentially be extracted to provide breathable air or to make rocket fuel. Some regions contain trace amounts of water bound to the dust, especially near the poles, where it may be preserved in the shadows. By learning how to work with the lunar surface material rather than against it, humanity might turn this seeming nuisance into an essential tool for survival and progress. The moon's dusty surface, then, is more than a simple layer of soil. It is a record of cosmic history, a challenge for exploration, a potential resource, and a defining element of the lunar environment. Every footprint left by astronauts is preserved in it, undisturbed by wind or rain, silent marks that may last for millions of years. The dust is the moon's memory, a blanket of history that speaks of impacts, silence, and time on a scale that dwarfs human imagination. The moon, Earth's constant companion in the sky, has a fascinating characteristic known as synchronous rotation. This means that the time it takes for the moon to spin once on its axis is exactly the same as the time it takes to orbit once around the Earth. Because of this perfect match, the same side of the moon always faces us, while the other side, often called the far side, remains hidden from view. To stand on Earth and look up at the night sky is to see the same familiar face of the moon that people thousands of years ago also saw, unchanged through the ages. This fact, simple in its observation yet complex in its causes, has shaped not only our understanding of celestial mechanics but also our cultural imagination. Synchronous rotation is not unique to the Moon. Many satellites in the solar system share this property. It arises from a process called tidal locking, which occurs over millions or even billions of years. Early in the history of the Earth-Moon system, the Moon likely rotated more quickly and showed different sides to Earth. But the gravitational pull of Earth created tides in the Moon's rocky body, just as the Moon today raises tides in Earth's oceans. These tidal bulges gradually exerted frictional forces that slowed the Moon's rotation. Eventually, its spin slowed enough to match its orbital period, and at that point the balance became stable. Once this synchronization was achieved, the Moon no longer rotated freely relative to Earth, but instead became locked in this eternal dance, always keeping one hemisphere toward us. The side that faces Earth is richly familiar, dotted with dark plains called Maria and bright highlands that have inspired countless myths, stories, and scientific inquiries. The far side, however, remained a mystery until the 20th century. For all of human history before the space age, no one had ever seen it. When the Soviet spacecraft Luna 3 sent back the first images of the far side in 1959, the world was astonished to discover a landscape strikingly different from the near side, with far fewer Maria and more rugged highlands. Synchronous rotation had hidden this world from our eyes for millennia, making it one of the last great geographical revelations of modern times. This arrangement has profound consequences for the Earth-Moon system. Because the Moon always shows the same face, radio signals from Earth cannot easily reach the far side without the help of relay satellites. For this reason, placing instruments or future human bases there requires additional planning. At the same time, the far side offers unique advantages. Shielded from Earth's constant radio noise, it provides a perfect environment for sensitive radio telescopes that could probe the universe without interference. The Moon's synchronous rotation thus not only defines our view of it, but also creates opportunities and challenges for exploration. The cultural impact of this fact is just as significant as the scientific one. The permanence of the Moon's face has made it an enduring symbol in art, poetry, and folklore. People have imagined shapes on its surface, from the man in the moon to various animals, creating stories that passed from generation to generation. This would not have been possible if the Moon constantly spun to reveal new sides. Its synchronous rotation gives us a celestial constant, something that connects us with ancestors who looked at the same patterns long ago. Even though we always see the same hemisphere, the Moon is not entirely motionless in the sky. Because of its slightly elliptical orbit and the tilt of its axis, it rocks gently back and forth in a phenomenon called libration. This allows careful observers over time to glimpse as much as about 59% of the Moon's surface from Earth. Still, a full 41% remains forever beyond direct view, accessible only through space exploration. This subtle reminder underscores the strangeness of synchronous rotation. What seems familiar hides an entire unseen world just beyond our sight. The Moon's synchronous rotation is therefore more than a quirk of orbital mechanics. It is the outcome of billions of years of gravitational interaction, a stabilizing force in our relationship with the Moon, and a defining feature of how we experience it from Earth. It explains why the Moon feels so constant, why one side was shrouded in mystery until recent decades, and why our cultural imagination has been so deeply shaped by a single, unchanging lunar face. To look at the Moon is to witness the silent effect of tidal locking, a reminder that celestial motions are not random but shaped by forces that bring order and rhythm to the cosmos. The Moon is more than a bright companion in the night sky. It plays a crucial role in keeping Earth's climate and environment stable by acting as a stabilizer of the planet's tilt. Earth does not spin perfectly upright on its axis but is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is responsible for the changing of the seasons, the lengthening and shortening of days, and the varying intensity of sunlight across the globe throughout the year. Without the Moon's steadying influence, Earth's tilt would be far less stable, and the consequences for life on our planet would be profound. The tilt of a planet's axis, known as obliquity, can shift over time under the influence of gravitational forces. For Earth, the primary stabilizing force is the pull of the Moon. Its gravitational interaction with our planet acts as a counterbalance against the tug of other celestial bodies, particularly the Sun and Jupiter, which could otherwise cause Earth's axis to wobble chaotically. Because the Moon is relatively large compared to Earth, unusually so for a satellite, it exerts a significant influence, keeping Earth's obliquity confined to a narrow range of variation. Over tens of thousands of years, Earth's tilt oscillates gently between about 22 and 24.5 degrees. A manageable shift that contributes to natural climate cycles but does not throw the planet into climatic chaos. Without the Moon, Earth's tilt could vary wildly. Models suggest that it might swing by tens of degrees, perhaps as much as 60 degrees or more. Such instability would create extreme and unpredictable climates. In one epoch, the poles might tilt toward the Sun, creating tropical conditions in regions that are now frozen. In another, the equator could experience freezing cold while the poles baked in constant daylight. These shifts would happen over thousands or millions of years, but they would drastically reshape the development of ecosystems and the possibilities for life to adapt. The relative steadiness we now experience, with predictable seasons and long-term climate patterns, has provided a stable foundation for the rise of agriculture, civilization, and complex societies. The Moon's stabilizing role is also closely tied to the story of life on Earth. Stability in climate has allowed life forms to evolve in consistent environments, without the constant pressure of sudden, extreme planetary shifts. While natural climate changes still occur due to factors like volcanic activity or variations in Earth's orbit, the broader framework has remained relatively steady thanks to the Moon's presence. This steadiness has helped ensure that Earth remains habitable across geological timescales, even as other planets like Mars or Venus have experienced dramatic environmental changes that made them less suitable for life. The origin of the Moon itself is thought to be linked to a giant impact early in Earth's history, when a Mars-sized body collided with the young planet. The debris from that collision coalesced into the Moon, and from that moment, Earth's fate was profoundly altered. Without the Moon, Earth would not only lack tides as we know them, but also the stabilizing force that keeps its tilt from swinging into dangerous extremes. In a very real sense, the Moon has been a guardian of Earth's habitability for billions of years, shaping not just the rhythms of the oceans but also the rhythms of life. This stabilizing influence continues into the present and the future. The Moon is slowly drifting away from Earth at a rate of about 4 centimeters per year, and this gradual change may eventually reduce its ability to regulate Earth's tilt. However, this process is so slow that billions of years will pass before its effects become significant. For the foreseeable future, the Moon will continue to steady Earth's axis, maintaining the conditions that support life. The fact that the Moon acts as a stabilizer of Earth's tilt is a reminder of the delicate interplay of forces that make our planet habitable. It shows how something as seemingly distant and passive as a satellite has been, and continues to be, essential to life on Earth. Every season, every harvest, every migration of animals follows patterns made possible by the quiet pull of the moon. Far from being just a silent companion in the sky, it is a guardian of balance, ensuring that Earth remains a world of predictable cycles rather than a planet of wild and destructive swings. The moon, Earth's closest celestial neighbor, holds a unique distinction as the brightest object in the night sky. Its radiance is so familiar and constant that it often feels ordinary. Yet this brightness is extraordinary when considered more closely. Unlike the stars, which shine with their own immense energy, the moon does not produce any light of its own. Instead, it reflects the light of the sun. Its surface, covered with plains of volcanic rock, dusty highlands, and scattered craters, catches the sunlight and sends it back toward Earth. This reflected glow is what gives the moon its luminous presence, outshining everything else in the night sky except for rare appearances of nearby planets like Venus. Even then, no celestial body can rival the moon's dominance over the dark heavens. The moon's brightness is measured by its albedo, or reflectivity, which is actually quite low. Its surface reflects only about 12% of the sunlight that strikes it, far less than Earth's reflective clouds and ice. What makes it appear so bright to us is its proximity. At just under 400,000 kilometers away, it is vastly closer than any star or planet, and so the light it reflects reaches our eyes with unmatched intensity. It is a reminder that brightness in the sky is not always a matter of how much light an object produces, but how near it is to us and how directly it can reflect the sun's rays. The phases of the moon further enhance the drama of its brightness. When the moon is full, positioned opposite the sun in the sky, it presents its entire near side illuminated, and the night is bathed in silvery light. On such nights, landscapes can be seen clearly without the need for artificial illumination, and shadows stretch across the ground as if it were a dim version of day. In contrast, during the crescent or new moon, its brightness dwindles, offering only a sliver of light or none at all. The rhythm of waxing and waning brightness has been a natural timekeeper for human societies, marking months and guiding calendars long before the invention of mechanical clocks. The brilliance of the moon has shaped human culture in countless ways. For ancient people, the glowing orb was a source of wonder and mystery, inspiring myths about gods, spirits, and supernatural powers. Farmers planned harvests by moonlight, sailors used its glow to navigate across dark seas, and poets turned to its silver brilliance as a symbol of longing, beauty, or melancholy. Even today, the moon's brightness draws the gaze of casual stargazers and professional astronomers alike, its glow reminding us of the bond between Earth and its companion. Scientifically, the brightness of the moon also affects life on Earth in subtle ways. Many animals have adapted their behaviors around moonlight. Some predators hunt more actively during bright nights, while prey animals may hide to avoid being seen. Sea turtles, for example, are known to navigate by the glow of the moon reflecting on the ocean's surface. For humans, bright moonlit nights once extended activity into hours that would otherwise have been restricted by darkness, influencing patterns of work, travel, and social life before artificial lighting transformed human existence. At times, the moon's brightness changes in dramatic ways. During a lunar eclipse, when Earth comes between the sun and the moon can dim to a coppery red as sunlight filters through Earth's atmosphere and scatters. These rare events remind us that its glow is borrowed light, dependent on the sun's position. Yet once the eclipse passes, the moon resumes its place as the sovereign of the night sky, reasserting its dominance over all other lights. The fact that the moon is the brightest object in the night sky is more than just an observation. It is a key part of how humans experience the world after sunset. Its reflected light creates patterns of time, inspires cultural traditions, influences natural life, and connects us to the wider cosmos. Each time the moon rises and casts its glow, it brings continuity between past and present, between science and myth, between Earth and the heavens. Its brightness is not only a physical reality, but also a constant presence in the story of humanity, an enduring light that defines the night. The surface of the moon is marked by countless impact craters, making it one of the most distinctive and recognizable features of our nearest celestial neighbor. To look at the moon through even a modest telescope is to see a world scarred by collisions, each crater a reminder of the violent history of the solar system. Unlike Earth, where erosion, weather, and tectonic activity gradually erase the evidence of ancient impacts, the moon has no atmosphere, no running water, and only limited geological activity. As a result, craters that were formed billions of years ago remain visible today, preserved almost perfectly in the stillness of lunar dust and rock. Craters form when meteoroids, asteroids, or comets collide with the moon's surface at tremendous speeds. The lack of an atmosphere means that incoming objects are not slowed down or burned up, as they often are on Earth. Instead, they strike the ground directly, releasing energy with explosive force. In an instant, rock is vaporized, dust is thrown outward, and a circular depression is carved into the surface. Some craters are small, only a few meters across, while others span hundreds of kilometers. The largest, such as the South Pole Aitken Basin, stretch so wide that they dominate entire regions of the moon, testifying to impacts of unimaginable scale in the distant past. The craters are not only scars but also windows into the moon's geological history. Their density and distribution allow scientists to estimate the relative ages of different regions. Surfaces covered with countless overlapping craters are ancient, dating back billions of years, while smoother areas with fewer craters, such as the Lunar Maria, are younger, formed when volcanic activity filled older depressions with dark basaltic lava. By studying crater patterns, scientists can reconstruct the timeline of events that shaped the moon, and in turn, better understand the history of the solar system. The appearance of craters varies widely. Some have sharp, well-defined rims, while others are eroded by the constant bombardment of micrometeorites that slowly grind rocks into fine dust, known as regolith. Many larger craters feature central peaks formed when the ground rebounded upward after the impact. Others have terraced walls or ejecta blankets, fields of debris spread outward from the point of collision. Together, these features give the lunar surface its rugged, textured look, visible even to the naked eye from Earth. The familiar patterns that people imagine as the man in the moon or other shapes are largely formed by the contrasts between cratered highlands and the smoother dark plains of volcanic origin. For much of human history, people did not understand the origin of these craters. Some thought they were volcanoes, others imagined them as markings left by gods or supernatural beings. It was only in the 20th century, as scientists studied impact physics and sent spacecraft to observe the moon up close, that the true story became clear. Missions such as Apollo confirmed the impact origin by bringing back rock samples fused and altered by colossal collisions. What had once been a mystery became a record of cosmic violence written plainly across the moon's face. The abundance of craters also makes the moon an important laboratory for science. because Earth's surface has been reshaped by erosion and plate tectonics. Much of its early history is lost. The Moon, however, preserves that history in stone. By studying its craters, scientists learn not only about the Moon but also about Earth's past, including the period of heavy bombardment that may have influenced the emergence of life. The Moon serves as a kind of archive, keeping a record of billions of years of impacts that shaped the solar system. For astronauts who walked on the Moon, the craters were not just distant features but part of the immediate environment. They climbed their rims, collected samples from their edges, and marveled at the stark beauty of landscapes shaped entirely by impacts. The silence and stillness around these craters made them seem eternal, as though time itself had stopped. Today, they continue to fascinate both scientists and the general public, symbols of a world so near to us yet so different from our own. The fact that the Moon's surface is covered in impact craters is not merely an observation about its appearance. It is a key to understanding its history, a record of cosmic events preserved in dust and stone, and a reminder of the dynamic forces that shaped not only the Moon but also Earth. Each crater is a story of collision and transformation, part of a collective memory etched onto the lunar surface, where it will remain for ages to come.